I will do only one question from homework. So pick it carefully. What is it that I will do? Choose wisely. And your choice is? No choice? Where is Dami? He was here.
Number 6.
You are choosing number 6. Number 6, I choose you. Is that it? Yeah. What's so special about 6?
The shape, but actually, it's number 4 and 3 that are the ones that have 3 different materials and the heat is being transferred through them.
There's 3 materials, yeah, okay.
Yeah, and then also the one that has the shapes.
Shapes?
Yeah, could you do like 2? Explaining the one that has shape and the one that has 3 different materials.
Okay, I'll do 2, but I may stop the answer as soon as I get to a part where you could finish it by yourself. Do you know what I mean?
Yeah.
The calculation, yeah. All right. Bello, could you read? Which one do you want me to do first? Number 3? Okay, go for it. Read it out to us.
A 0.1 kg brass weight at a temperature of 98.5 degrees Celsius is placed into a well-insulated copper can of mass 0.185
0.185
kg,
kg.
containing 0.342 kg of water at temperature of 20.2.
342 kg?
Yeah,
At temperature of what?
20.2.
Okay.
Assuming no heat is lost to or gained from the surroundings, determine the final steady temperature of.
Cool. Okay. So basically, you drop your brass into the water. Yeah. Now, because the water is at 20.2, I also know that the copper can is at 20.2 as well. I mean, if the copper can was warmer, it'd be warming up the water. And if the copper can was cooler, then the opposite would be happening. You know, if you leave the water in the can, the two will reach the same temperature. Thermal equilibrium. Okay. Now, what will happen when I place the hot brass into this? What will happen to the water? And also, therefore, the copper can will heat up as well. So, the brass, will it gain or lose energy? Lose. The water, gain or lose? Gain. And the copper? Gain. Now, are we given the heat capacity of things?
Yes.
Yeah, okay. So, how much energy does the brass lose? Well, that would be M. C, what's the C for brass?
0.38 times 10 raised to the power 3.
And the temperature. Initially it's at 98.5, and then will it rise or fall? Fall, let's say it falls to X. Yeah, equals. Now, the water gains energy. M. What's the C? 4181, and what do they use?
0.3.
For the water.
4.18 times. Oh yeah.
4.18 times. Yeah. And the temperature change, it increases from 20.2 to T. Yeah? Or to X, I mean.
That's a change temperature to Kelvin.
Don't have to. You'll get the same answer in this question. It's fine if you do, though. Plus M of the copper. What's the C for the copper?
2.4 times 10 to the power 3.
That's x minus 20.2. They're the same, if you can't see. This is where I'll stop. Because what am I left with as a problem? What type of problem? No, it's not even quadratic, it's linear. It's linear. You expand, you group the x's, and you solve. Think you can manage that? Yeah. Expand, group, solve. Yeah. It's okay? Yeah. Yeah, this one's a little tricky. But once you have the equation set up, it's fine then. Right, what was the other one you said, Bello?
Number 6.
6? Okay, go for it. What's 6?
It starts like it's a drawing of
Yeah?
a 3D projection of like a H.
A H? The letter H? Oh, is it like a steel beam or something?
Yeah, something like
And it goes back?
yeah,
Okay.
and it's dimensioned.
You know what it is. Okay. And what are we told?
It says the diagram above shows the cross section of the
Mhm.
steel grinder used to hold up a roof.
Okay.
It measures 15 centimeters wide
Okay.
and 15 centimeters in height.
Okay.
All other dimensions are 5 centimeters.
Ah, okay. So basically they're saying this goes 15, 5, 5, 5, 5, 5, 15, 5, 5, 5, 5, 5. Yeah, okay.
What is the cross-sectional area of the grinder?
Right, so I'm looking at it as this rectangle, and this rectangle, right? So that would be 0.15 times 0.05. That's this rectangle here. And there's 2 of them. Plus, yeah. 0.05 times 0.05. Right, so what's that area, please? Zero point 175 meters squared. Right, what's the next part? Hello?
The length of the grinder is 2.25 meters.
What's the volume?
Given that the density of steel is 7,800
Yeah.
kg meter cube, show that the mass of the grinder is 30.
Okay. So you know that density equals mass over volume, right?
Yeah.
So what does mass equal? Density times volume. What did you say the density was?
7,800.
Yeah. And the volume will be the area times the length. What's the length? 0.2. 2.2.
It's in meters.
Yeah. So what do we get as the answer here?
7.1.
Is that what they said it should be?
Yeah.
Okay.
If a crane is used to lift a grinder at a constant speed to a height of 20 meters in a time of 2 minutes, what is the minimum power of the electric?
Okay. So power equals work over time. What work is being done? It's being given. It's lifting. It's been given potential energy, which is mgh over time. What's the time? 2 minutes. What's the mass? 307.1. What's the G? 9.81. And Bella, what did you say the height was?
65 meters.
And out we go.
One six three
163.
1.85.
Okay. Watts.
What's
Yeah.
Sorry, 25.
Ah.
Yeah. 2 questions are.
Okay. 25. Fine. Right, so what happens 20...
6 to 8 watts.
Okay, what's the next part?
If the grinder were to fall from a height of 25 meters
Yeah.
to the ground, and all...
Yeah, how much hotter is it? Yeah, we've seen this one before, haven't we? So what happens? This is like Joule's experiment, isn't it? The potential energy gets released and becomes heat. Potential energy, mgh. What is the m? It is 307.1. What's the g? 9.81. What's the h? 25.
Isn't it minus in this case?
No, no,
This is falling.
no. And that's equal to m. What's the m? 307.1. The c, what's the c?
400.
Delta theta. Can you get the delta theta? Of course you can. Are we finished? Yeah. Seriously, where did Danny go? Like, did he say anything when he left, or he just disappeared? Is his stuff still there? Oh, he might have skipped out on Stephen's class, huh? He might have said, "Smell you later, guys." Alright. Naughty, naughty. Okay. Do you have that? Are we okay with that? Yeah. We'll continue. Yeah. Now, before I start, two things. Number one, I didn't have time at the end of the class yesterday to do the experiments with you for that lesson. It was the experiment for how you actually calculate the, where's it gone? The specific heat capacity. Like, how do people calculate that number? Okay. There are two experiments. How to calculate it if it's a solid, like the example earlier with the brass, and then how do you calculate it if it's a liquid, like water or oil. Now, I put, just this morning, I put 2 links at the bottom of the Moodle page, one for each experiment, which you can read in your own time. If you don't want to read the web page, what you could do is you could look at the video from the intake 1. Whereas in that class, I had time at the end to explain the 2 experiments, okay? So your choice, whichever you prefer to do. They're not really that difficult. The experiment for measuring the heat capacity of a liquid is actually very easy. The solid is a little harder, okay? It's at the very bottom of the Moodle page. There, yeah, those 2 experiments. Yeah, but you can also watch the video from intake 1. So the video would have been uploaded sometime in October last year, because that would have been when they did it, about maybe November, sometime like this. You can find it, I'm sure, on my YouTube channel. You could, yes, actually, you can go to their playlist. You should be able to see it. Yeah, good idea. So, can you either use Moodle or YouTube later to add those to your notes? And I am going to check in the next physics class that you've copied some notes down for these experiments, okay? Is it because I don't trust you? Yes. Yes, it is. All right, let's look at